Alrighty, folks. So, picking up where we left off the other day, changing gears again, and remembering that this lecture is, it's not just a random slew of topics. There is some connection. They're all Earth sort of things. And a lot of it came from, we get 3/4 through the semester, and I say, well, remember what we talked about? And you'd be like, we didn't talk about that. It's just these random sort of one-off things that are tangential to other topics. And it just accumulated into this lecture. So they share that in common, so to speak. So where we're headed now is talking a little bit about the seasons, believe it or not, on such a wonderful day as this, where it's blowing ice sideways. Well, it stopped blowing ice sideways, but talking about how we the solar energy budget, as it were, and so on and so forth. So when I started giving this lecture years ago, nobody had a flashlight on them. Occasionally you get somebody with one on their keychain or something like that. And now that everyone has a flashlight on their little pocket computer, I've got all the blinds open, and we still really can't do this because I'm not going to close out all the sunlight right now, what we have of it. So what I'm going to tell you is to try this experiment at home, which is what I've been saying for 25 years. When you get home later, try this. You folks at home, try this. So you actually start with the flashlight that's in the back. All right. I understand why they put it in the back. It's visually more, effective. But that's our first step. And you want to get a piece of paper. A white piece of paper is fine. Pencil, and you need a partner. Now you can probably do this as a thought experiment in your head, but it's kind of cool to see it, and it's not hard to do. So, at any rate, so you hold the flashlight, foot and a half off the table, okay? And you want to note its brightness, and maybe even draw a circle around the beam. All right, hold it up however high you need to be to get it, the size of a jar lid kind of, circle. And again, note its brightness. Then we want you to turn the flashlight so that beam is now coming in at an angle. All right. And again, we want you to trace that beam and note its brightness. Now, as I said, this isn't too complicated. You could do this in your head more than likely. What do you think the difference in the beam brightnesses, if any, is going to be? From the circle to it makes an oval when you turn it sideways, right? That's what they're trying to. I had hiccups for some reason. They could have tilted it a little further, but you see how one is a circle, one is an oval? You think that's going to have any effect on the brightness of the flashlight?
The more slanted it is, the less bright.
Why?
Because it has more area to light up.
Okay. So what she said, if you didn't hear her, was that the area of brightness, the circle is going to be brighter than the oval. I followed that up with how's come, and she said, well, because you've got the same amount of light going over a bigger area. All right, again, you don't have to do this physically, but you should. It's surprising the difference, I guess, is the one arguable reason to do it. The energy from the flashlight hasn't changed. Okay, it's the same amount of photons or whatever you want to say coming out of there. Just the intensity. So that is supposed to be analogous here to the sunlight coming into the Earth's surface. And while you are tempted to think, perhaps, that that this is a circle, in any given spot on that circle, arguably it's flat enough, so on and so forth, because of our tilt, because of a handful of things, all right, this sun's energy hits the Earth more directly at the equator and just above it and just below it than it does the farther north or the farther south you go. All right, and it's curvature, and like I said, a couple other things we bring into effect here. So, again, something you already know, we're telling you the reason for. The areas around the equator and just north and just south of that receive a lot more bang for buck with the sun's energy than you do as you go norther or souther. Okay? That's why. Now, you can't quite see it in here because, well, it's just not that big. But we've got the words equator in the center there for 0 latitude. We've got Tropic of Cancer, 23.5 north of there, and Tropic of Capricorn, 23.5 south. And the tropics there, that designates the tropics zone. All right. Looks a little wider than maybe you thought it was, but it is a good chunk of the Earth there. We're going to be talking a lot more about that. You say something?
Oh, makes sense to me.
Okay. Okay, good.
Big old light in the sky there. Probably
Well,
covers
yeah.
a lot of space.
Yeah. Fair enough. All right. We're going to talk about this slide for a very long time. And again, while you do have access to this, some things you might want to make note of conversationally here. So, as the title indicates, what we're talking about here are the seasons. All right. And what we're really looking at is, the more you stare at this, the more you'll probably process that, is how the sun's energy moves between the tropics. All right. Now, it's a circle, it's a cycle, it's going forever and ever and ever. We could start anywhere, but there's typically a logical place to start. In spring semester, I start on the left, and in fall semester, I start on the right. All right? Because those were our most recent solstices. What do you guys already know about a solstice? What is a solstice going to mark, or what does it do or tell us, or however you want to say it?
Whether we have more sunny days or more, actually, no, it like shortens how much sunlight we have in a day.
Okay. Anyone want to add to that? I don't have a whole lot of anyone's today, but which one's the short, which one's the long? Do we remember that?
It's the winter solstice is when we start getting like more sunlight in the day, and then summer solstice is when we start getting like shorter sunlight in the day.
You explained it entirely backwards, but that's totally awesomely true. No, that's a depressing way to think about it in some ways. Most people would say that the summer solstice is the longest day of the year. But you're absolutely right, though. It is after that day, they start getting shorter. I have an uncle. He's very dark humor, and my family has a cabin back in Ohio, and when we can, we get there for big 4th of July celebration. They spend way too much money on fireworks and just have a good old time. And every year, by the end of the day, he's had a beer or two, and we're sitting there, and I'm catching up with him. He's 80-something now. And he's like, I don't know why everyone's so damn happy. I'm like, why is that, Uncle Dan? He says, well, from here, it's all downhill. What are you talking about? He's like, well, very soon it's going to be the solstice, and then we're going to start losing light, and so on and so forth. He says, summer's practically over. I'm like, oh, stop. Yeah. So, well, no, actually, we're past the solstice. I should say it's pretty soon. It was June. Now we're clipped off the board here. See, we try and zoom to get you guys. Well, so we're going to talk about that. We're going to talk about the dates. Where is the? Oh, it's right next to me. The remote. They bounce a little bit. All right. You see the solstices? Oh, I can't aim it at the board. I can't aim it at the projector. All right, got nothing in between. So the solstices are both labeled as 21. You look at your equinoxes for a minute, since you brought it up. One of them's on the 20th, one of them's on the 22nd. And again, they do sort of bounce. We'll throw a leap year in and messes some stuff up here and there. For this class, we normalize everything at 21, okay? Now I know there's those teachers out there and they've scarred many people for life. It's like, is it March 20th or is it March 21st? Wrong! No, just, you know the month, you know the approximate day. You could Google it from there, okay? So, like I said, we normalize stuff when it comes to the multiple guess questions on the test, and they will be there, all right? You're really thinking about the month and what season goes with that, which by 20 years of age, you should have that part down, you guys. So at any rate, so back to summer solstice. So summer solstice is the longest day of the year. Winter solstice is the shortest day of the year, which you are absolutely right. Again, by the time we get to that winter solstice, at least me, I'm not a winter person, and I totally hate how dark it gets so early. I know that we get 2.5 seconds each day, starting on the 22nd, more of sunlight. Does it take a while for that to add up? It sure does. But at least mentally, I can tell myself we're getting there. All right. So, anywho, so we're going to start at the winter solstice, which is the shortest day of the year. And we're going to move towards the spring equinox. All right. And you do see that this happens to be the way the Earth rotates around the sun, too, which is kind of nice. What do we know about equinoxes? Does that word mean anything? Anybody? All four of you? All right, so equal and nox is night. Equal night. So it's days when it's supposed to be 12 and 12 for sunlight and darkness. Okay, and we hit, huh? Yeah. Again, there's some latitudinal adjustments. My Earth Science class does a really cool lab where we actually look at real solar data and we track when this stuff really happens. And it's kind of, I don't know if they find it cool, but I think it's kind of neat. So what's happening then is we move from I didn't ask you guys. So on the winter solstice, where is the sun's energy shining most directly? They're trying to give you a hint or a tip there by tilting the globe. Not at us. Right. You may have heard when you were a kid growing up, the seasons are reversed with the southern hemisphere, northern hemisphere. Okay, this is why. All right, the sun is shining most directly at 23.5 south on the winter solstice. As we move to the spring equinox, where do you think the sun is at the equinox, you guys? Half. Do we have a half line marked on these globes anywhere? Yes. Big dashed white line with letters next to it. Shares the first 3 letters. 4 letters. Then someone else should be at no page. There are 3 more people here. Come on, you guys. Where's the sun headed to as we move from the solstice upwards to the... No, I don't mean that. Yes, but that's not what... Equator. Yeah, equinox. Equator. Yes, that was the answer I was looking for. All right. Yeah, sometimes you guys are overthinking things. You're like, oh, no, it can't be that. Yeah, no. All right, so we're bouncing from 23.5 south to 0, the equator. All right. At the equinox in March, that is the official start of spring. All right, and that's why I joke whether or not the groundhog sees his shadow or not. There's always 6 more weeks of winter in Utica, and I think you got even from February 2nd, which is when Groundhog Day falls, to get to March 20th, the official start of spring. You actually have longer than 6 weeks, but it's not about necessarily. Well, it is about where the sun's energy is, but you know how we get those warm spots here and there anyhow. That's what they're really kind of talking about. So anywho, so light is increasing. Okay, daylight length is increasing. You hopefully have noticed that now. It's no longer dark at 4:20, thank God. All right, and we're moving up where the majority of the sun's energy is shining at the equator. From there, it just keeps on trucking, okay, as we move from the spring equinox, which, by the way, we use the word vernal. Vernal. I said spring, V-E-R-N-A-L. It is not on here, but that will be on the test. All right, vernal. They don't change summer and winter, but for some reason the equinoxes, they have fancy words for it. Anywho, so from the vernal equinox, moving on to the summer solstice. Look at the Earth tilted there. And on the summer solstice, the majority of the sun's energy, or more of the sun's energy, I should say, is tilting in the northern hemisphere, and that is our summer. All right. And that is also our longest day of the year. And as the doom and bloomers point out, from June 21st, which leaves you a good chunk of summer, because you guys, growing up, are still in school, all right, by that point, typically. Summer's already on its way downhill. Days start getting shorter, and that keeps on going through until almost the end of September, when we have the autumnal equinox. That one's not so bad. At least you've heard the word autumn before. All right, not necessarily vernal for spring. That's a new one, but autumnal sounds like autumn. The autumnal equinox, the sun is moving back down from 23.5 north to the equator. You're back to 12 and 12, arguably, so you're still not complaining. But you notice once school kicks back in, those summer nights, especially if you guys like to barbecue and all that stuff, you have dinner, by midsummer you're eating dinner at like 8:30, at least at our house, because it's still light out and everybody's running around still. But by fall, when that kicks in, you're like, geez, okay, no, we got to start going back to 5:30, 6 o'clock if I want to grill, because the sun's going down. So we're back to the equator. And then as we move from the autumnal equinox to the winter solstice, again, it just keeps going down, back to 23.5 south. Okay? And it does that, thank goodness, on and on and on every year, no matter what we do. It keeps doing its thing. Now, a couple things to note here. Okay, again, solstices, we just say summer and winter. The equinoxes, we've got vernal for spring, autumnal for fall. You want to remember December, March, June, September. And those roughly line up with the seasons. Utica's a little challenged, all right, mainly with the spring one. I grew up in Ohio, not even southern Ohio, but spring came a heck of a lot closer to the end of March than it does around here. You don't have to go that much south for this stuff to actually, make a difference. I don't know if you guys have noticed. I know sometimes you guys travel to Binghamton. We go the Albany way. Once you get into March, you go a little bit south, you'll quite likely find a good 10 degrees warmer, even just going, like I said, to Albany. So it doesn't take a whole lot of latitudinal change for this stuff to kick in. Mind you, it's a good bit further south, but we went down into mid-PA last spring, Easter time. My son was doing something there, and then we drove to my mother's back in Ohio. And the trees had buds on them already. And here we left, snow. So it's you get those changes relatively quickly, especially again with our vehicles. Anywho, so 23.5 north, 23.5 south have names. You're going to want to remember those names. I don't know how many times I took this quiz going up through. Arguably, I took a different path in college than some of you were going to take, but I was asked several times which one's a tropical Cancer, which one's a tropical Capricorn, and I could never remember. And it took to being a teacher and talking to you guys about it that I realized the damn things are alphabetical. So use that to your benefit. CAN comes before CAP, right? LMNOP, yeah. So Cancer is 23.5 north, and that's the crab, not the disease. Capricorn is 23.5 south. And you may have also heard that even though it's winter in the southern hemisphere, it's not quite as bad as our winter, so on and so forth. Look how far south, you got South America there in that top picture. Look how far south 23.5 south gets you. All right. So their winters, if you're on a continent, which is generally where you find people, they're still in the tropic zone technically for their winter, which is really kind of nice. Unlike us, where that kicks out just below Cuba, so or whatever little island dot that is there. But you get my point. Actually, that's below Cuba, but yeah, I think you get my point nonetheless. What are those next dashes? Way up top and way down at the bottom there. You can't really see the bottom one. Yeah, those are your circles. Okay. Sneeze here. Excuse me. And we don't need to worry about what's the word I want? We don't need to worry about degrees for that one. But you may have heard again about spending X number of months in total darkness, X number of months in total light. Again, if you look at the spin and you look how far north that is, you could probably believe how that happens a lot easier now. All right, they're just not. No matter what happens, they're not going to be pointed towards the sun. They're not going to get any energy. They're not going to get any light. So that brings us to the last thing I want to point out is that 23.5 degrees tilt, which is yet another number you're going to need to remember. Try to get through geology without you guys memorizing a whole lot of numbers, but this first test, there are some. So we are tilted 23.5 degrees off of straight up and down, okay? And because of that, that's why the tropics are where they are. That's why the sun's energy bounces in the way that it does. If we were straight up and down, the sun would always have the most of its energy shining essentially at the equator all year round. We wouldn't have seasons. And it would be much more sort of zonal, permanent climates, so to speak. Does that make sense? All right, it's because, and if you watch it, you actually, I wish this was animated. No, honestly, that would be really cool. I'm sure there's one out there. But if you look at the stop motion there, so to speak, you can kind of see how that tilt does play into everything. And I just want to end this with a little bit of math. So how many seasons we see in here? 4. How many months are there? 12. How many months per season is that? Mathematically 3. All right. There are places in the world, you guys, I just want you to know, and I want you to have faith and believe in this here. All right. There are places in the world where there's only 3 months of winter. Sadly, that means there's only 3 months of summer, but no, I jest. But honest to gosh, it is a latitudinal thing, okay? You guys grew up here. Again, you may be horribly fond of winter, and I'm not, trying to badmouth it or anything like that. But if you grew up, like I said, even in southern New York, you would see a different distribution of stuff. It's a latitudinal thing, okay? You may have friends that move to the south, family in the south. Again, you know this. But this is the reason why it is. Questions before we switch on? Like I said, a lot of questions, deceivingly, a lot of questions off of this slide. It was like half a dozen, maybe a couple more, I forget. All right, changing gears again. So we started, however many slides ago, staring at that picture of the Earth. And I said, what are you guys looking at? You said water, and I said, what's the white stuff? You said the air. Remember all that? Okay. So we're formalizing that up a little bit. We're going to introduce the words if you don't already know them. Heard them, but terrestrial, terra, the Earth. Aquatic, Water, aqua, you know that word. You may have noticed that it was mostly water. We are a blue planet. Okay? Nearly 3/4 of the Earth's surface is covered in oceans. About a quarter-ish, a third-ish, closer to a third, is land. All right? Terrestrial, terra. This is where the word extraterrestrial comes from beyond, above the terra, the earth. All right? All right. Radius of the Earth is approximately 4,000 miles. So from the average spot on the surface to the center is 4,000 miles. Remember, this is not diameter. It is also not circumference. What would circumference be? I don't mean a number, but what is the circumference? What does that measure?
How long it is around.
Right. So if we tried to put a belt around the equator or a giant rope, all right, that's the circumference. So we're not talking about that. We're literally talking about a straight line from the surface to the center. All right. And you know, twice that's where you get your diameter. So I just want to make sure everyone knows. Again, there are no math requirements for this class, so I want you all to understand what we're talking about. So approximately 4,000 miles. Not that far. Pain in the butt to get there, but not that far. Let's see. How far is it from Manhattan to Los Angeles? All right. So it's not even twice Manhattan to LA. All right. Which again is a hell of a drive. Don't get me wrong. It's not that bad of a flight. It's a long flight, but not that bad of a flight. So I like to put things in perspective every so often. So 2,700, if you didn't hear it, 2,700 miles from New York to LA. Of that 4,000 miles, we've gone 2. That may have changed semi-recently. Every so often I check and see. We've gone, with people that is, we've gone about 2 miles. I indicated the other day that things change drastically once you start to go into the earth. You've got pressure, right? And you've got heat. And the human body just isn't built for that kind of stuff. Again, maybe next time you're flipping through the channels and they're talking about people working the diamond mines in Africa or something like that, keep it on there for a minute or two and see these folks coming up. They weigh like 78 pounds. They're wearing a towel around their waist as the only clothing. And, you know, I bet they can out-hike any of us up here. That's some, you know, you seriously act, they're like a different pole of the Sherpas, you know, who have got all their amazing abilities for high altitudes. These folks haven't acclimated themselves to going down into the earth. It's tough. So there's a reason we haven't been that far. Now, we've drilled a good bit deeper. And again, I haven't checked on this number yet, more recently. But still, out of 4,000 miles. All right. That's like, huh?
We're not meant to go up or down. We're land creatures.
Yeah, we are land creatures, yes, for sure. But that's like going, you know, from that trip from Manhattan to LA and stopping at, I don't know, Secaucus to pee or something. I mean, you just barely touch the surface. You're there. Also, you know, if we could somehow get into the crust, I'm a big fan of Jules Verne, Journey to the Center of the Earth, and there's all kind of neat stuff we need to see and find out about.
Second sun down there?
Yeah, we'll see. There's some interesting stuff. They did find oceans now, they're telling us, so we'll see. What was I going to say? I mean, you only have the crust, and then you're into the mantle anyhow, and as far as we can tell, and we'll talk about that in a moment, as far as we can tell, you know, you're into this Play-Doh-y kind of material, silly putty kind of material, because it's elastic and stretchy. Play-Doh is just malleable. So how do we know all that stuff? How do we know all that stuff? We don't really need these. We'll keep this up for a minute. Don't worry about the MOHO stuff yet. But I just want to keep this while we're talking here. Well, I can actually work this into it. So the MOHO line, or the Mohorovicic discontinuity, you can see why we shortened it to MOHO line, not just me, marks the boundary between the crust and the mantle. All right? Back when we started doing atomic testing, they realized, A, those bombs were shaking the entire planet. Not good. Yeah, big bomb, big boom, big shake. Not only were they shaking the entire planet, but since we had our seismographs, can I say seismograph? You guys kind of know what I'm talking about? No? Okay. So seismographs are those things you see in movies when they either are going to have an earthquake in the movie or some big boom happens somewhere. It's that strip of paper that's going across with the red pen that starts bouncing on. It kind of looks like the EKG thing, but it's for the Earth, okay? And it goes, starts shaking like crazy, drawing a bunch of scattery lines. That's a seismograph. A seismologist is someone who studies earthquakes, geophysicist. All right, so when those things are drilled into the bedrock, they're all over the place. Every cool college has one, and then some kind of things, okay? So we started realizing that these waves, the seismic energy from these bomb explosions, yes, it was shaking the whole planet. Yes, it was traveling through the Earth, but different stations were getting the information at different times, and something wonky was going on. And they had always known, well, because the Earth cracks and bleeds occasionally, we knew it wasn't solid all the way through already. There's lava or magma in there, right? Every kindergartner drawn a volcano. They know somewhere in there there's puddles of molten stuff. So we knew that was down there, but it really helped us to figure out where that boundary was. And that boundary ended up being the Mohorovicic discontinuity. So please don't concern yourself with these velocities. Okay? But maybe you can guess. Do you think those sound waves travel better through solid rock or through molten rock? Molten? Anybody else? What would you travel? Well, yeah, that's sort of because what would you travel better through? Difficult traveling through either of those, but if you had to, arguably you could probably get through molten. Think of it more as being on the surface. What can you run better on, a paved road or a muddy trail? Paved road. So the waves travel better through solid rock, and when they hit the molten stuff, they slow down and get all wonky. So they were able to figure this all out. And that's what these velocity zones, that's what they're talking about on there. All right. So how do we know? We've been all of 2 miles. We're telling you an awful lot of stuff. We're going to be talking about plate tectonics. We're going to have you memorize the layers of the Earth. And we've been 2 miles. We don't know. Well, there's indirect ways of finding stuff out. And is it 100% right? Probably not. But it's, again, going back to the nature of science, it's with the best minds right now working on this, it's what they think is going on. That's where the information we're giving you. So why? Did I skip a slide? I guess I did not. So why is it molten in there? Why does it get hot for those diamond miners? Well, the Earth's core. And again, you probably had an idea of that. All right. It comes from radioactive decay in the Earth, also generates heat. All right. Radiation is energy being given off. We tend to associate radiation, again, with something nuclear and bad, and radiation gives you cancer, and all that's true. But everything around you, every moment of every day, is decaying and giving off energy. It's not all bad for you, so to speak, okay? Everything is breaking down all the time. And when you're in the Earth like that, it's sort of a cooler. People never think about that. You always try to keep stuff cold in your cooler. You could actually keep stuff warm in a cooler, too. This is the same thing that helps it keep stuff cold will keep stuff warm. It's insulated. That's why it works. So the Earth insulates and keeps a lot of that energy in there. The main problem is that most coolers aren't set up for like a casserole or something, right? You have to turn it sideways. That's why we hardly ever use it. There's some money to be made there. You make a horizontal cooler for grandmas to bring casseroles to picnics, you'd make a ton of money. A ton of money. And I get a cut, please. All right. Anywho, how hot is it? It's upwards of 9,000 degrees. How do we know that? Math. All right. We told you the other day we had a number for the temperature decrease in the atmosphere. Anyone remember what we called that? Okay, by the test you need to, though. That was the lapse rate. All right. Now we have something called the geothermal gradient, which is an increase in temperature as we go into the crust. A lot of vocab words coming out of this lecture. A lot of vocab. So the geothermal gradient, we've got it roughly a 1 degree per Fahrenheit for every 70 feet. I don't know if that was sarcasm or not, but it's, it's not huge, but it does add up because you got a lot of feet to go. We got 5,280 feet to a mile. We got 4,000 miles. It could get warm. I've not done the math. Going to assume you could actually get somewhere near 9,000. I'm also probably fairly confident that it's kind of logarithmic and not linear as far as that goes. Yeah, it's got to start jumping exponentially at some point. So there's exceptions, all right? You've probably been in a basement before or a cave, all right? It doesn't start right away, this increase in temperature. There is this sort of ambient underground temperature that if you're truly underground, and that's why sometimes basements get so cold because part of it is not underground, it's exposed. If you could truly, have a basement that has no exterior access and so on and so forth, it could bounce around this ambient temperature, which I want to say is 58 degrees, 62 degrees, I forget. But there is sort of an ambient temperature, like where, again, caves and whatnot. That's why we first inhabited caves. We found not only protection from the elements, but that they tended to be a good bit warmer than just sitting out there in the snow on a rock or even under a fir. Well, there's another exception to the rule, and that is when the hot comes to us. All right. We talked already about the earth cracking and bleeding, volcanism. All right. Sometimes the magma leaves the mantle and comes up very close to the surface. You get these hydrothermal features like, where the heck is Old Faithful? It just jumped out of my head. National Park, famous for the geysers. Yellowstone. All right, you get places like Yellowstone and a handful of others, and that's because there's a giant pool of magma under there in the crust, really close to the surface, heating up the groundwater. But otherwise, these are pretty standard rules. There finally is the diagram you've all been waiting for, and yes, I do you right by putting that on the test so you get at least a couple gimme points on there. Hopefully you knew there were 2 layers to the core nowadays, crust, mantle, core. Not just crust, mantle, core. Inner core and outer core, all right? I don't know if this one's to scale or not. Mine, I have the outer core a good bit narrower. I don't even know. I might have the numbers in a minute here. I don't know. Yeah, well, this is for people my age, this is a very comforting diagram, I think because of the colors. They're very 70s and 80s colors, and it's just I'm a kid looking at 3rd grade or science again or something. I don't know. But yeah, so this is quite possibly a common diagram. I Googled it from somewhere. I should have cited it, I suppose. I'm going to assume it was open source. Well, you don't have to change it much to make it look the same, but So let's talk about each of those things there. The crust. All right. First and foremost, we want to remember that the crust is broken into two types. You've got continental crust and you've got oceanic crust. Now, these are rocks that you probably don't know their names of yet, but you will. And if you did really well in Earth Science a few years ago, you might remember them. All right. So the ocean is made up of something called basalt. It's an igneous rock, and it is dark black. And you will come to know it, love it, and hate it by the time we get to the rock test. The continents, on the other hand, are made of something called granite. Again, you probably have an idea what granite is. Everyone has granite countertop nowadays. Suffice it to say that very few of those countertops are actually granite. I will save that rant for when we get to igneous rocks in lab, probably. But granite. What will be important a little later is that those guys have different densities. Basalt and granite have different densities, and that leads us to why continents are higher than ocean floors. I don't need you to memorize these depths, but just in case you were wondering, they're here. I do want you to remember the granite and basalt, though. Why do they actually abide by that, or what? Or you know the names? They have the ocean as basaltic and the continent as granitic. Good for Minecraft.
At least I can dig in the mountain and find too much granite.
Okay. Underneath the sedimentary rock first, huh? So beneath the crust, we have the mantle. And as I said earlier, it has a consistency of silly putty. And that might seem like a silly thing to say. And honest to gosh, we really did used to say Play-Doh. But the more they study it, the more they realize that it has an elastic sort of property to it, which silly putty has and Play-Doh does not have. We haven't been there. They're studying the heck out of it. And I don't know that much about geophysics. It's very far. I do critters and surface processes, okay? But again, the folks that do dig this kind of stuff, this is what they believe. This is what their data shows. You don't say belief in science. But, excuse me, so this is what we're going with. Even the mantle isn't consistent. All right, we talked about density changes earlier. So we talk about the upper mantle. That's important because of plate tectonics. We'll give you a word for that in a couple minutes, actually. The middle mantle and the lower mantle. Important to very few people on the earth, but, you know, some of them do care about it. And they're called geophysicists. We used to say the mantle is molten. We're trying to move away from that. It's not. You wouldn't say that silly putty is molten, right? It's malleable. It's elastic. It's a handful of things, but it's not molten. And part of that, you talked about pressure a little bit ago. Part of that has to do with pressure. All right, pressure does a lot of funky things. It was in chemistry. I remember when you go through your gas laws and everything like that. It's something you got to account for. Lastly, the core. Yeah, and I don't have dimensions here. I didn't think I did. So we have the outer core, and we talked about this on day one. Okay, we talked about the magnetosphere, and that is a function of because the outer core is molten, the inner core is solid, and the one sloshes around the other, creates energy. Here it is. They're both mostly iron, with a little bit of nickel and a handful of other things mixed in. I get there's something called density separation that we'll talk about eventually. Density separation tells us that the heaviest stuff settles out. This is the reason you ideally shake up the jug of orange juice before you pour yourself a glass of it, because all the pulp and everything, all the good stuff is down on the bottom. And when you're in a sphere, down is the center, right? So all the heavier stuff settled out as the earth was cooling. So I get that there's iron in the center. What I don't get are these, we'll just allude it, we'll call it temperature differences. But how we go from the solid rock, again, I get that's on the outside, it's far away, that makes sense. The mantle, okay, it's in between. It's kind of, that nougaty kind of stuff. Okay, I'm again fine with that. Then we get to completely molten liquid, metal. And then we get to completely solid metal. And the solid makes sense going back to pressure. Again, there's so much pressure by the time you get there. I don't get the molten part. But again, it's not on my end of things, but maybe not, maybe. And somebody might know, and I just don't know. But what did he say about it?
But that's what it does.
Oh, but that's what it. Oh, yeah. It is what it is. It is what it is. You guys probably use these words in their science. Lithosphere and asthenosphere. We're in college now, so we can't just keep that diagram crust, mantle, core. Okay? Not even crust, mantle, core. We need to add in 2 more. So there is crust, mantle, core. There's 6 more points on the first test. I've told you practically half the test at this point. The lithosphere is on top. Excuse me. Shouldn't eat while I'm trying to lecture. A lot of people think when we talk about plate tectonics, it's the crust floating on the mantle, and arguably you're fine saying that. Technically speaking, it's the lithosphere floating on the asthenosphere. What's different is that the lithosphere has a little bit of the mantle included in it. Next time you crack an egg and you are trying to get all that goo off the shell, that's what we're talking about. Okay? The shell is the crust, and that little bit of goo that just won't come off no matter how hard you shake it is that little bit of asthenosphere stuck onto the lithosphere. Okay? And that is broken into pieces that we call plates. So it's not the crustal plates. They said that for many, many years. Technically speaking, again, it's lithospheric plates. And that is resting on or floating on what we call the asthenosphere. Now, in geology, we're coming up on minerals now, and we've got this wonderful mineral called sphalerite, and that's a tough consonant cluster for some of you guys. We don't have that SPH too often. But we really don't have the astheno a whole lot either. So this is possibly the hardest pronunciation word so far here. Astheno. And again, I'm sure it is a prefix. In Latin, it means something. And I should have Googled this one because I dig that kind of stuff. But so this is that bit of mantle, the middle mantle, all right, that is below the lithosphere. And this is important because plate tectonics. Now again, plate tectonics is sort of a hidden science. They see the effects of it on the surface. We know the continents are moving around. We know how fast they're moving. We know what direction they're moving. And we've got a pretty good idea why. It's called convection currents. All right? And they know that's happening in the mantle. They've narrowed it down, they think, to the asthenosphere, but there's still people out there arguing that there are lower mantle currents driving, picture gears getting from big to little and so on and so forth. Lower mantle currents driving these middle mantle currents. Again, maybe we'll sort it out one of these days. May keep them employed till their end of days. But important to think, again, that the asthenosphere is not all the rest of the mantle. Okay, there's still that lower mantle that we really don't care about. All right, so lithosphere and asthenosphere, let's put that all together. I tried to keep the same color scheme. Didn't do quite as well, though. The right side of this diagram is old school. Crust, mantle, core. The left side of this is the lithosphere and the asthenosphere. So, having said what we just said, what do you think A is pointing to? All of you together, come on. A is, I just said it. Lithosphere. Yeah, yep. Right side is, so look at the lines there. We got some thicknesses on the left. So if A is the lithosphere, B must be supposed to be asthenosphere. Good. All right. Now we jump to the other side. Where's the crust? D. All right. Good. C is mantle. Which one is outer core? AB, leaving E to be inner core. Why AB, you're probably wondering. Well, you guys just got out of 12 years of standardized testing. You know that they only go A, B, C, D, E. So I had to come up with a way when I have more than A, B, C, D, E, more than 5 answers. And boy, you would not believe, or you might believe because you just came out of 12 years of standardized testing, the stress that causes when I would have you guys bubble in 2 dots in a row. I would have people come up and say, I can't color. When I did those tests, I hand graded them. Okay, I briefly went to online testing. We still need to talk about what we're going to do. I think I'm going back to paper and pencil with you guys. But you folks at home, obviously, you have to be online. But so AB is a remnant of that. And if I needed another answer, it would be AC. But I just felt so bad that I could see you guys twitching when you go to color a second dot in the same row it's not allowed. So yeah, they'll slap your knuckles with a ruler or something. But so that's why AB and not F. Okay, this is an old test diagram that I decided to color in. So again, A is lithosphere, B is asthenosphere, C is mantle, D is crust, E is inner core, AB is outer core. And yeah, if you go into that not having heard this lecture or paid attention during this lecture, I can see how you would get confused with A being crust and so on and so forth. But all right. So as I said, we've been chatting a little bit about plate tech already. We do have an entire chapter on it that ideally we get to. So I simply need to introduce it right now. Plate tectonics has really evolved since I've been a student and since I've been a teacher. Plate tectonics, the theory hasn't evolved, but how important we view it has changed. Well, first of all, when I was in school, they still said the words continental drift. The textbooks said continental drift. But you know the old joke about how outdated high school textbooks are and so on and so forth. Back in the 80s, it was even more true than it is now. You guys might only go 5 years or so with the textbook. They were pretty old back then. Plate tectonics has been a word since the late 60s, okay? But it just didn't work its way into the mainstream for a while. So, anywho, so we heard about continental drift, and that was a toughie because the guy was so right, Al Wegener. He was actually a geographer, meteorologist, I think, as well. And he had the luck of traveling around and seeing the world, and he just saw so much that looked similar. And looking at maps, you've heard the old thing about it looking like puzzle pieces and so on and so forth. He had evidence, though. He had, if you put it back together, look, these mountain ranges line up. Look, you have the same sorts of rocks on the seams, the same fossils in the same sorts of rocks when you line the mountain range. I mean, all kinds of. But he had no mechanism. He had no way for it to all to happen. And he had the unfortunate luck of presenting this paper for the first time to a whole bunch of geophysicists. And all they wanted to know was, Al, how the hell is this going to happen? What, do you think these continents are floating around in the ocean? Well, no, but and obviously it stuck, continental drift, okay? He didn't have a way for it to happen. Then, as technology got better, we got our cool little magic yellow submarines. We're floating around in the ocean, and we started finding these spreading centers. We realized that the crust was getting bigger. We found these other areas where the crust was going down into the earth and getting destroyed, and we realized we were living on conveyor belts, okay? They figured that part out. He was long dead, unfortunately. But as we said a couple moments ago, we're still not entirely sure how it works. We've got GPSs nailed into Mount Everest and here and there and the other thing. We know these things are moving. We know what direction. We know how fast and so on and so forth. So it's not a question of is plate tectonics anymore, but it is definitely still a how. Neat stuff. Neat stuff. So as we said, the lithosphere is broken into pieces called plates. The lithosphere rests on the asthenosphere. And a word you hear way too much without me necessarily explaining it, plate boundaries. Okay, that's where one plate ends and another plate begins. They're the seams or the gaps. Okay? And plate boundaries is where, so I started to say our thinking about it has changed. So when I started high school, we didn't even call it plate tectonics. By the time I got to college, plate tectonics was a thing, but it was like the last chapter in the book. And if the teacher got to it, the teacher got to it. And then all of a sudden, at some point, it's like chapter 2. And it's been chapter 2 for a good 10, 15 years now. I think it's 2 in your book. They moved it to the front of the book. Because what we used to do was say, okay, so remember all this crap we just talked about? It's because of plate tectonics. Have a good summer. See you next semester. Whatever. Now, they start by saying, okay, this is what plate tectonics is. This is how it works. This is this. This is that. And now we're going to talk about all these neat different things that it causes. Volcanism, earthquakes, current location of the continents, mountain building. Different side of the same coin. With all the stuff we have to talk about, I still keep it at the very end of the semester. But just in case, there's a handful of semesters we don't get to it, I give it 10 minutes now, like we are. And that way I've at least talked about it, should we not get there officially. So, now that I've mentioned it, I could say, hey, remember plate tectonics, what we talked about at the beginning of the semester. But you don't know the nitty-gritty. You don't need to know the 6 different ways a plate can move right now to get through the rest of this semester, in my opinion. So we got half a dozen, 7 large plates, and a bunch of little ones, okay? Imagine, again, going back to that egg conversation. You drop an egg, you're going to have big pieces of shell, you're going to have little pieces of shell. All right, it's the same idea. Nobody dropped the earth, don't get me wrong. But as it cracks, okay, and where the big pieces more or less line up to your continents or your oceans. Sometimes the cracks are in the middle of something important. Sometimes they're in the middle of nowhere. Generally speaking, at the cracks, we've got stuff happening. Those are the active areas. In fact, they call stable continental interiors that for that very reason. In the middle of the U.S., there's no plate boundary. We don't see volcanoes and or earthquakes. And sometimes. We'll talk about that when we get to earthquakes. All right. And there's certainly evidence of volcanism out there as well. So there used to be some stuff. But nowadays, the majority of that activity focuses around these plate boundaries. And no, I'm not going to have you label a map. Don't worry about that. But you do have the North American plate, the Eurasian plate, the African plate, the South American plate. I'm hoping you could label those, should I ask you to, if you know where your continents are at any rate. The Pacific plate, huh? Yeah, well, I have had people not know which ocean is on the east and which ocean is on the west. So, well, there's that too. All right. So as I just implied, it is important because the following. And the past location of the continents. We've got a really cool animation when we do get to plate tech that I sometimes show. It goes back before, you guys all know Pangea, right? Yeah, Pangea was not the beginning. There was many iterations before Pangea. Pangea is just when the most recent supercontinent formed and broke up from there. Has anyone been lucky enough to see mountains other than the Appalachians, the Adirondacks here? Up here, you guys call them what'd you see? Okay, so you've seen the Rockies?
Yes.
All right. Which is more, no offense to upstate New York, but what's more impressive, the Rockies or the Appalachians? Rockies. All right. What were you going to say? You flew, where did you fly over them?
Yeah, I flew over them, but
Did you get to see them at all that much? Or? they're like 10 times more awesome than the Appalachians, but there's a really good reason why. Okay, why? Do you know?
The Appalachians are way older.
Yeah, incredibly older. Appalachians formed, and so we're totally not dissing them or anything. The Appalachians are ancient, and weathering and erosion. You guys know all about that. All right, Appalachians formed as Pangea was coming together.
The
Okay.
Appalachians are older than sharks, which are older than trees.
Yeah, there you go. That's an interesting kind of timeline there. I like that. All right. So, yeah, that's why they look. And the Rockies are super young. Okay, super young. Not from 100 years ago. They're millions of years old. But compared to the Appalachians, they're super young. And they do, if you drive out west, they just, they're there. Okay, and I know we've got a nice gradual. We're in the foothills of the Adirondacks, and it's lovely. It's pretty, don't get me wrong. But it's just like coming out of somewhere, and then all of a sudden you're in skyscrapers. So, yeah, the Appalachians are ancient. So Pangea, it wasn't the first thing, okay? So when what is now we call North America smashed into what is now called Europe, that mountain chain came to be. So, all right. At any rate, that is an hour, and we are shifting into our third and final gear of this lecture, which we're going to save for another day because an hour of listening to me is more than enough.